Now I further explain the policy gradient method. Reinforcement learning has another name is reward learning. Reinforcement learning describes the interaction between the agent and his environment. We formulate these reactions using the Markov decision process. To solve the Markov decision process, the most popular method is a policy gradient method. Now we go more detail to explain how policy gradient works in the reinforcement learning. Let's see here. This is the state. State means include the observation from a camera on the board of the robot. And the internal state includes the joint information and the torque inside the robot. We put them together as a state X. At this state, we have an action space. Action space includes all the possible actions for an agent can select under the policy. So we select the agent select this action under the policy. For example, can left turn straight or right turn. How can we select this action under the policy? Remember, right now, the environment is either can be static or is dynamic. So we select action under the policy in a different environment. We want to get the maximum reward. Once we get the maximum reward, then we say that action or that policy is an optimal policy we are searching for. Then I switch to the next state. So we select this, we find this or search for this policy is try to understand the environment, especially for dynamic environment. Make sure we have a maximum reward. Right now, because we have a deep convolutional neural network, so the network can help us. For example, this policy network can help us select this policy in this dynamic environment, get the maximum reward. That's the relation between the agent environment and how can we use the policy gradient, find this policy to reach the maximum reward. So right now why we are interested in reinforcement learning, because we want to let an agent, when the agent see or observes this situation and how the agent select action from under the policy to reach the maximum performance. Now let's go to the detail. For the policy gradient method, the idea is we need to define an objective function, and then we calculate the derivative of the objective function with respect to policy parameter state. Once we get this update, then we can get the new policy parameter. Okay, now let's see. To use the policy gradient, we define an objective function. Objective function, this is the probability distribution. This is a reward along a trajectory. Tau is a trajectory. From a Markov decision process, we can see this probability distribution can be expressed as this policy times this state transition probability. Of course, this distribution times this reward, we can get the reward from state xk to state xk plus 1. Once we have this objective function, then we can calculate the gradient of the expected or objective function. We got this one because our reward is not a function of policy parameter theta, so we can move out the operator. Then we use the ratio trick. This formulation is between the log and the derivative of log and the derivative of the function, the relationship. Then we can change the integral from this formulation to this formulation. Why we do that? Because right now we have this distribution, and use the Markov, use the Monte Carlo approximation. Then we can change the integral to expectation. So in this way, we don't need to calculate a complicated integral. Instead, we just calculate the expectation over the samples of the policy distribution. As we know, if we change the integral to expectation, then we have to consider the bias and the variance problem. So because this sample is along the trajectory, so we don't have a bias problem. However, because the sample is along a trajectory, we have a large variance. We use, use this relationship. So that means we can select any B as a baseline, insert to the gradient of the objective function, don't change the value at all. However, use this baseline, we can reduce the variance. That's the idea. So we got this baseline in this formulation. If we wish, you can prove this. We'll have a minimum variance. We change this from the integral to this sampling problem. For more details, please check with this reference. Thank you. Bye.